Imagine standing feet away from 300 tons of liquid metal, glowing white hot at nearly 3,000 degrees Fahrenheit. One wrong move or a single drop of water in the wrong place triggers a lethal steam explosion. The radiant heat coming off the furnace floor was so intense, regularly topping 400 degrees, that standard leather work boots would char and burn through in minutes. To survive, workers wore heavy, wooden-soled clogs. Wood provided thermal insulation and bought them a few extra seconds of reaction time if a splash of molten steel hit their feet. This was the reality of the open hearth era. For over 80 years, from 1868 to 1992, these massive, cathedral-like structures dominated American steel production without a single digital sensor or computer control. The physical skeleton of modern America, the bridges, the railroads, the skyscrapers, was forged entirely through immense human physical endurance and raw, primitive chemical intuition. To make structural steel, you have to solve a strict chemical problem. Iron fresh from a blast furnace, called pig iron, contains about 42% carbon. That makes it incredibly brittle. To become usable structural steel, the carbon content has to be boiled off and reduced to between 0.1 and 1.8%. That boiling process requires temperatures approaching 3,000 degrees Fahrenheit. The massive thermodynamic roadblock of the 19th century was that available fuels, like natural gas and heavy fuel oil, simply could not burn hot enough on their own to melt and refine the iron. To build modern civilization at scale, engineers needed to invent a machine capable of cheating the natural limits of thermodynamics. The solution was the open hearth furnace. Picture a massive, room-sized bathtub made of fire brick, covered by an arched roof, and holding up to 300 tons of liquid metal. The genius of the design came from engineer Carl Wilhelm Siemens. He created a regenerative system. Beneath the furnace floor sat two massive chambers, packed floor to ceiling with fire bricks arranged in a crisscross checkerboard pattern. As the furnace burned, hot exhaust gases were directed downward into one of these checker chambers. The bricks absorbed the extreme heat from the waste gas, storing that thermal energy like a giant thermal battery. After about 15 minutes, a series of sliding valves reversed the entire airflow. Now, incoming cold combustion air passed through those superheated bricks, picking up enormous amounts of thermal energy before it even reached the furnace, allowing the fuel to finally burn near 3,000 degrees. By recapturing up to 80% of its own waste heat, this brilliantly simple brick architecture made the mass production of industrial steel economically viable. Feeding those furnaces was punishing work. Predominantly Eastern and Southern European immigrants worked grueling 12-hour shifts and ambient floor temperatures that regularly exceeded 120 degrees. Every 2 weeks they worked a long turn, a continuous 24-hour shift to swap the day and night schedules. Because they had no electronic instruments to measure the chemical makeup of the steel, operators relied on the art of sampling. A senior worker, called the first helper, would dip a long-handled spoon into the bath, scoop out a sample of the boiling metal, and pour it into a small mold. Once the small ingot cooled, a worker smashed it with a sledgehammer. The melter foreman would inspect the broken metal, reading its grain structure, color, and fracture pattern with his bare eyes to estimate the exact carbon content of the 300-ton batch still cooking in the furnace. This tacit, unspoken human instinct was the only fail-safe dictating the structural integrity of materials that would soon hold up thousands of human lives. After 12 long hours of chemical choreography, the melter gave the order to tap the furnace. Workers knocked out a plug in the rear wall, surrendering the entire heat in a single irreversible act. 300 tons of liquid steel poured out in a blinding orange-white stream. The liquid cascaded into a massive brick-lined ladle below, throwing off a violent shower of sparks and forcing workers in dark-tinted goggles and asbestos jackets to stand far back from the blast. That raw liquid metal was quickly cast and rolled into structural elements of the modern world. It became the skeleton of the Empire State Building, the suspension cables of the Golden Gate Bridge, and the armor plating for the naval fleets of the Second World War. The tap hole ritual was the exact moment where raw earth, intense heat, and extreme human endurance fused together to create the physical skeleton of the 20th century. But the open hearth era did not last. Its executioner arrived in 1952, with the invention of the basic oxygen furnace in Austria. By blasting pure oxygen directly onto the molten iron instead of standard air, the basic oxygen furnace completed the exact same conversion in just 40 minutes. The open hearth took up to 12 hours. American steelmakers fell into an incumbent trap. Sitting on top of massive, expensive open hearth infrastructure, they delayed modernizing. Meanwhile, Japanese and European steelmakers, rebuilding from scratch after the war, installed the much faster basic oxygen technology immediately and devoured the market. When the American steel industry ultimately collapsed in the early 1980s, the human damage was catastrophic. Hundreds of thousands of steelworkers lost their jobs, and entire towns that had built their social fabric around these massive furnaces over 3 generations were hollowed out almost overnight. The rise and fall of the open hearth furnace proves that no industrial lead is permanent. As America looks to reindustrialize today, The steel mills of the past offer a clear lesson. Dominating the future requires a balance of human grit, chemical mastery, and the unforgiving willingness to adapt before it's too late.